Swayam Prabha. Digital India. Educated India.
Welcome to lecture 6 in this NPTEL online certification course on bioreactors. In the last lecture, we had looked at enzyme kinetics. We derived the expression for the Michaelis-Menten enzyme kinetics, and we also assigned a problem, a practice problem 2.1. Let us solve that problem in this lecture. The problem read as, let me make it full screen here. An industry scientist is studying a novel method of disposing a toxin that results from cell culture during the course of cultivation. The aim is to enhance cell yields through toxin reduction and medium recirculation. The toxin does not affect cell growth of its if its concentration is below 7.5 millimolar. The particular toxin that she is studying, X, can be broken down enzymatically using the enzyme E. The breakdown was studied at 30 degrees C at a pH of 7.2, and the following kinetic data was obtained under batch conditions. The variation of X with time was given. In part A, you were asked to determine the Michaelis-Menten parameters for this enzymatic degradation, and part B, if the total enzyme concentration is tripled, will the medium contain toxic levels of X after 30 minutes. This was the problem that was faced. So let us go and solve this problem. The first question, our usual first question, what is needed? Part A, Michaelis-Menten parameters, which we know are Vm and Km. In the Michaelis-Menten equation, V equals Vms by Km plus S. Now I have dropped this square bracket for the concentration term. In other words, S without brackets is the same as the concentration of S here. It's a little cumbersome to write the square bracket every time, so I have dropped it. I am going to drop it from now onwards in this course. So what is known or given? The data on toxin concentration versus time. The toxin is the substrate here, right? The toxin is the substrate for the enzyme reaction. So we have S versus T. And we also know that from the lecture material in lecture 5, that the Michaelis-Menten parameters, the parameters, can be obtained from the slope and intercept of the Lineweaver-Burke plot. A Lineweaver-Burke plot is 1 by V versus 1 by S. Now, how to connect what is needed to what is given? We need velocities because we need to plot 1 by V versus 1 by S. For that, we first need V. When we are working with such a data, we can calculate the average velocity for each time interval. In this case, between 0 and 10 minutes is the first time interval, 10 to 20 minutes is the second time interval, 20 to 50 minutes is the third time interval, and 50 to 100 is the fourth time interval. We can calculate velocities as delta x divided by delta t, and we have times here corresponding to the concentration, but we don't have times corresponding to the rates. So what is normally done is the rate that is calculated is assigned to the midpoint of the interval. In this case, in the first case, the interval is 0 to 10, and therefore the average is 5. We calculate the rate and assign it to the time of 5 minutes and show that to you. V is minus delta S delta T, and in this case, the first case, at 10 it is 17.7, at 0 it is 20, so 17.7 minus 20. that is delta S, and delta T is 10 minus 0, so that we have there equals, this works out to be 17.7 minus 20 is minus 2.3, minus of minus 2.3 is plus 2.3, 2.3 by 10 is 0.23. 0.23 in millimole, okay, this has been given in millimole per minute. So we need to assign it to the midpoint of 0 and 10 that we saw was 5 minutes. So at t equals 10, I see t equals 5 minutes, the substrate concentration, if we assume that it varies linearly in this time interval, okay, that's an assumption that we are making, which turns out to be good if we have closely spaced points. Let us see, this will be some sort of an estimate here. Some points are widely spaced, but anyway, this is the data that we need to work with, so let's do the best that we can with the data. So the midpoint, rather the substrate concentration that corresponds to the midpoint t equals 5 minutes is 18.85, which is the average of these two, and that is what we need to assign. Then V2 is between this and this, 15.8 minus 17.7, 20 minus 10, the negative of the whole thing. That turns out to be 0.19 millimole per minute, and we need to assign it to the midpoint, even the substrate concentration there, because we are plotting 1 by V versus 1 by S here. Okay. So the midpoint of 10 and 20 minutes is 15 minutes, and the midpoint, assuming that the decrease is linear in this regime, 17.7 and 15.8, the average is 16.75. So t equals 15 minutes, S equals 16.75, and so on and so forth. To get these numbers, 5, the V that we calculated was 0.23, the corresponding S at 5 minutes was 18.85, assuming linearity. At time t equals 15 minutes, S is 16.75, V equals 0.19, and these two calculations we had seen in detail. The same way we get these values for 35 minutes and 75 minutes, which are the midpoints of those corresponding intervals, S midpoints of the corresponding linear variations, and V that was calculated, the average rate that was calculated in that interval. So now that we have this, we need to plot 1 by V versus 1 by S. 1 by V versus 1 by S is what we need to plot. We have V and S, therefore we need the inverse values of that. If we invert 18.85, 1 by 18.85 happens to be 0.053. You can verify the calculation. Tell me if there has been a numerical error somewhere. The inverse of 16.75 is 0.06. The inverse of 13.2 is 0.076. The inverse of 7.8 is 0.128, or 1 by that. Similarly, the inverses of V, 1 by V, is 1 by 0.23, 4.35, 1 by 0.19, 5.26, 1 by 0.173, 5.78, and 1 by 0.112, 8.93. Okay. Now, it's best to use spreadsheet to plot. You can use a graph sheet to plot, you can use a spreadsheet to plot. Let me show it to you using a spreadsheet. Right. We have let me go to the problem. Yes. We have 1 by S, the values on this column, and 1 by V, the values on this column. If we plot a graph between 1 by S and 1 by V, these are the same values that we saw in the table earlier. If we plot this 1 by V versus 1 by S, these are the points that we get. Now this spreadsheet MS Excel allows us to use or allows us to draw a best line fit, a line fit, the best line that fits to these points. This is the best line fit here with the least squares value of 0.9879, and the equation of the line, which I've asked to display here, is 58.348x plus 1.4559. Y is 1 by V, x is 1 by s, so 1 by V is 58.348 into 1 by s plus 1.4459. You would have done this in your calculation or to find that out. You could have also used a graph paper, that's okay. If you do that, then you should end up here this is the same graph, right? And the slope happens to be 58.35. The software would give you a large number of digits, but we need to choose the digits that are of relevance to us. Let us choose just the 2 digits here after the decimal point. Slope is 58.35, and we know that in a Lineweaver-Burke plot, the slope equals Km by Vm. Therefore, Km by Vm is 58.35, and the intercept we know as 1 by Vm in the Lineweaver-Burke plot, that happens to be 1.46. I'm rounding off this large number of digits here to just two digits after the decimal point, 1.46. So from this we can find out Vm and Km. You know that simplest thing is the inverse of V, 1 by 1.46 would be Vm, and therefore Vm is 0.69 millimolar per minute. And now that we know Vm, we can substitute it here and calculate a Km. Km happens to be 58.35 into Vm. Km by Vm is 58.35. Therefore, Km is 58.35 into Vm. That turns out to be 58.35 into 0.69 or 40.26 millimolar. Okay. So these are the Michaelis-Menten parameters. Vm, which is 0.69 millimole per minute, and Km, which is 40.26. That was part A. We still have part B left. Same questions for part B. What is needed if the total enzyme concentration is tripled? Will the medium contain toxic levels of X after 30 minutes? We need to find that out. What is known or given? The toxic level of X is 7.5 millimolar. The concentration of X at time 0 is 20 millimolar from the table. We know that the Michaelis-Menten equation governs the rate of this reaction. We know the Michaelis-Menten parameters from part A. All this we know. And now we need to connect what is needed to what is given. How do we do that? We need to find the time taken for S or X. Our toxin is S here, toxin X is S here, to reach 7.5 millimolars from 20 millimolars at initial time, right? If that time happens to be more than 30 minutes, yes, there will be 7.5 millimolar or more when 30 minutes are up. If the time happens to be less than 30 minutes, no, the medium will not contain toxic amounts. So to find S, we need to recognize that V is the rate at which S is disappearing in this batch process, right? V equals minus ds dt, the accumulation rate of the substrate, the negative accumulation here, equals Vms Km divided by Km plus S. If we solve this differential equation, minus Km plus S by S ds equals Vm dt, we are considering slightly, the solution of the differential equation, right? We need to get all the variables, appropriate variables to one side, all the s's on this side. We have done that. Km by S plus 1 minus of that ds is Vm dt, and integrating we get minus Km ln S plus S is Vm t, and the limits of integration are S naught to S for S and T naught to T for T, and T naught happens to be 0. Therefore, if we integrate that, this term is minus Km ln S by S naught plus S minus S naught. It goes from S naught to S, therefore S minus S naught equals Vm into T minus T naught, or Km ln S by S naught plus S naught minus S is Vmt. When the total enzyme concentration has been tripled, what essentially happens? The total enzyme concentration, the new total enzyme concentration is 3 times the old enzyme concentration, total enzyme concentration. But what does total enzyme concentration affect that is of relevance to us? It's the Vm dash, or the Vm, the maximum rate. We know that Vm is K3 into Et, right? So Vm dash is K3 into Et dash. So this is what is going to get affected when the total enzyme concentration is changed. Okay, that is the key concept here for solving this problem. Once we recognize this, the problem is done. So Vm, we have a new Vm here, Vm dash, that is K3 into 3 times Et, that will be 3 times K3 into Et, or 3 times Vm, or 3 times 0.69, which happens to be 2.07 millimole per minute. The rest is straightforward. We have the variation of substrate with time here, given here that we derived. We just have to substitute it into that expression. If we substitute 40.26 km ln of 20 by 7.5, the conditions of our interest, the 7.5 millimolar is a lower level. We need to find out the time it takes to reach 7.5. We have substituted the other numbers here, and the time turns out to be 25.1 minute. Okay. This 25.1 or 20, it takes about 25 minutes for X concentration to reduce to 7.5 millimolar, starting from 20 millimolar. Okay. And 25 minutes is less than 30 minutes, and therefore at 30 minutes there will be no toxic amount of X left. Okay. So we have solved this particular problem. I think we should stop here and then continue with lecture 7 later. See you in lecture 7.